Hello again, chemistry students. We are now ready to move on to our final topic of the year. And so we're going to go ahead a few chapters. And so we're going to go now to chapter 18. And this chapter, we're going to talk about the ever so important acids and bases. And so we're going to go ahead and start off today with an introduction to acids and bases. We will also be doing the homework in class, so you will not have any homework to do tonight. A few things that we'll be looking at today. What are the physical and chemical properties of acids and bases? How we classify solutions, whether they're acidic, basic, or neutral. We'll talk about the important scale we used for that. And then we'll also discuss 3 different models of acids and bases, all named after scientists who first described them. So we have Arrhenius, Bronsted-Lowry, and Lewis models. And so we'll talk about what each of those means as well. So we do have some definitions, but we'll go ahead and we'll define those today. And then once we're done, we will go over the homework in class. And so let us now go ahead and get started with our final chapter of the school year. And this was on acids and bases. Some properties of acids and bases. On the left picture here, we have things such as vitamin C, we have citrus fruits like oranges and lemons, we have aspirin, we have vinegar. Any of these, if you were to taste them, are going to taste a little bit sour. And so we know that one of the physical properties of acids is that they taste sour. And so also think about like your soft drinks. So if you think about carbonic acid, phosphoric acid, the citrus fruits I mentioned, lemons, limes, and grapefruits, all contain citric acid. And so, again, the acids will give these foods a bitter or sour taste. Bases, on the other hand, if we look over here on the right, we have Drano pipe cleaner, we have milk of magnesia, we have ammonia. Bases taste bitter. And so I do want to remind you guys before you start to think about this, it's never a good idea to drink anything or eat anything in the lab. And so just through history or just by accident, people discovered that bases taste bitter. And so they're also a good way to think about this. Basis starts with B, and so does the word bitter. So B with B. And so we have a strong base of sodium hydroxide, which is oftentimes called lye, L-Y-E. Ammonia, sodium hypochlorite, which I will tell you personally I can't stand the smell of. This is what's found in bleach to help clean clothes. Notice that many of these bases are used as household cleaning items. And so many of you have both acids and bases within your own homes. And so this is another reason why it's important to maybe study this, because they are pretty much everywhere that we look. All right. We need now to get down to the atomic level, and we have to kind of understand what is going on to make something more acidic or something more basic. All right. An acidic solution is going to focus in on hydrogen ions. And so a hydrogen ion is a hydrogen atom that has lost its one negatively charged electron. And so by losing the one negatively charged electron, hydrogen ion takes on a positive 1 charge. Basic solutions contain a lot of what are known as hydroxide ions. And so if you guys remember from last semester when we were looking at ionic bonds, I had you guys memorize those 14 polyatomic ions. And so one of the ions I had you memorize was hydroxide. And so as the name suggests, it has a hydrogen, it has an oxygen, and notice that it is negative 1 charged. And so what happens then, if we put an acid together with a base, we end up with what's called a neutral solution. And so this can undergo what's called a neutralization reaction. And so the last topic in this chapter will have us look closer at those types of reactions. I do want to let you guys know, neutral reactions involve an equal amounts of acids with base. When you add an acid and a base together, you will always form a salt and good old water. And so, for example, we have HCl, which is hydrochloric acid, which is also the acid you find in your stomach. We have sodium hydroxide. So again, we can see that there's the OH. Over here we have the H for the acid. We have what, as you remember from chapter 9, we have a double replacement reaction. And so the Na is going to trade places with the H, and then the Cl is going to trade places with the OH. And so we end up forming two new products. We form the salt sodium chloride, and then we also again form H2O. And so an acid plus a base will always produce a salt and water. This model of acids and bases was first proposed by the Swedish chemist Svante Arrhenius. I'm sorry, I apologize for my terrible Swedish accent. What he proposed was that an acid produces these hydrogen H plus ions, while a base produces the hydroxide ions, or also known as OH minus ions. And so, for example, hydrochloric acid, if given enough time, will break down or decompose into hydrogen ions plus chloride ions. Or sodium hydroxide as a base can break down into a sodium ion plus a hydroxide ion. And so we know then that this is an acid because it produces hydrogen ions. We know that this is a base because it produces hydroxide ions. However, it's not a perfect model because, for example, if we look at ammonia, although it doesn't contain OH minus or hydroxide ions, we know that it is a base. And so this model is a very simplified model for acids and bases, but we need to see if there's a better way to describe it. Two scientists working together, Bronsted on the left, Lowry on the right, came up with another model of acids and bases. What they proposed was that an acid is an H plus hydrogen ion donor, very similar to Arrhenius' definition, and the base is a hydrogen ion acceptor. And so if you really think about this, what is this a restatement of? And of course you guys would probably know that I'm referring to the law of conservation of mass, because if the acid loses the hydroxide ion, or hydrogen ion, then the base is what picks it up. So remember, nothing is ever lost or gained, it's just moved around. And so this is basically, again, a restatement of Lavoisier's law of conservation of mass, because the hydrogen ion that's given up by the acid is then taken up by the base as its acceptor. And so, for example, we have hydrochloric acid plus ammonia forms the ammonium ion plus a chloride ion. And so, since HCl loses its H plus ion to become Cl minus, it's the acid. The NH3 actually ends up gaining a hydrogen. So notice it's going from 3 to 4 hydrogens, and therefore it becomes NH4 plus 1 because it's gained of H plus. Therefore, this is the base. And so this definition is a much more useful definition of acids and bases than Arrhenius. But again, we had to have them start somewhere. All right. A third type of model for acids and bases is by Lewis. And so if Lewis sounds familiar, it's because we already talked about him when we were looking at electron dot diagrams. And so those are the Lewis dot diagrams that we have to show electrons getting moved about. And so it's the same gentleman. According to him, a Lewis acid is an electron pair acceptor, whereas a Lewis base is an electron pair donor. And so I do want to let you guys know, for those of you who are going to be interested in something in the medical career in the future, one of the prerequisite classes you'll need to take is organic chemistry. And so you will be using Lewis acids and bases predominantly in that particular class. And so I'm just going to give you guys a heads up now. You will be seeing this concept again if you decide to take OChem in college. In the above reaction, we can see that the fluoride atom donates one of its valence electrons to boron trifluoride to form the boron tetrafluoride. So in this case, because it's donating the electron pair here, this is the Lewis base, and because the boron trifluoride is accepting the electron pair, it becomes the Lewis acid. And so again, this is our product for this. So this would be boron tetrafluoride ion. And so this is, again, another model of acids and bases. All right. Looking at these types of reactions, we can see that there are related compounds that result because of the transfer of hydrogen ions from the acid then to the base. A conjugate acid is the species that's produced when a base accepts a H plus ion from an acid. And so these will always be found on the right side or product side of the equation. The conjugate base, as you would expect then, is the species produced when an acid donates the H plus to a base. And so let me show you how this works. Notice that the acids and bases are always on the reactant side, and the conjugate acid and conjugate bases are on the product side. So that's always the way it's going to be. Notice that we have the acid is going to be paired up with the conjugate base because notice the acid is HCl, the conjugate base has the H removed, and therefore that's why it's Cl minus 1. So the acid is joined up with the conjugate base, therefore the base is then joined up with the conjugate acid. So notice we have ammonia, which is NH3. Over here, the conjugate acid is NH4 plus because this has taken up the H plus ion from the HCl. And so the acid is joined up with the conjugate base, and the base is joined up with the conjugate acid. So again, the difference here lies in the hydrogen. So the acid has an additional hydrogen that the conjugate base lacks. The conjugate acid has an additional hydrogen that the base lacks. And so that's how you would be able to distinguish these different parts of this type of reaction. All right, I'm going to finally talk about different types of acids and bases. And so this also is important because when, again, you can look at the words to pretty much tell you what you're dealing with. The prefix mono refers to one, and the prefix poly refers to many. And so a monoprotic acid can donate one and only one H plus or hydrogen ion per molecule. And so some examples of this would be hydrochloric acid, hydrobromic acid, and chloric acid. And so notice each of these only have one H. And so by only having one H, they can only donate that one H plus ion. And therefore, that is why they're considered monoprotic. All right. A polyprotic acid, as the poly would suggest, can donate two or more hydrogen ions. And so in examples of this, we have sulfuric acid. So notice the formula for sulfuric acid is H2SO4. So it could donate two hydrogen ions, which makes this diproduct. And then we also have phosphoric acid, which has the formula H3PO4. And therefore, this can donate up to 3 hydrogen ions. And so this is triprotic. All right. Why should you care about this? In your body, in order to help you maintain proper pH homeostasis, and so all my anatomy students will get that reference, you will see that there is a buffering system that relies on both carbonic acid, H2CO3, and bicarbonate ions, HCO3. And so basically, if your body gets a little bit too out of whack for its pH levels, these will be kicked in then to help restore balance to your body. And so again, that is what that's in. All right, and so what I'd like to do now, I want to go ahead and do the problems in the book for this section, and so you will not have to do these problems for homework tonight. And so the problems we're going to do are going to be problems 1 and problem 3. All right, so let's go ahead and first we're going to look at problem 1. So problem 1 is on page 635. number one asks to write balanced equations for the reactions between the following. And so we're given aluminum and sulfuric acid. So we're given aluminum and sulfuric acid. All right, we know because we have the two reactants, we're going to end up with two different products. And so let's go ahead first and write out the formulas for each of these compounds. Aluminum gets the symbol Al, and means we're going to add these together. And the formula for sulfuric acid is H2SO4. Right. So what would you suspect is going to happen? Notice we have an element here. We have sulfuric acid here. This would be an example of a single replacement reaction. So the aluminum is going to come here. It's going to kick off the H2. So this is going to kick this off. And therefore, we're going to form two new products. We're going to end up forming AlSO4, aluminum sulfate, and hydrogen gas. And so notice, however, Al is 3 plus, SO4 is 2 minus. And so again, in order to balance out the ions, we have to perform crisscross applesauce. The 2 comes down here. The 3, because this is a polyatomic ion, we have to remember to put the parentheses around the sulfate. And then we're going to also add hydrogen gas. And so, are we done? No, because notice that this is not quite balanced. Notice we have aluminum, we have hydrogen, and we have sulfate. So I'm going to go ahead and put this here. So aluminum, hydrogen, sulfate. On the reactant side, I have just 1 aluminum. On the product side, I have 2. Hydrogen, on the reactant side, I have 2. And on the product side, I also have 2. Sulfate, I'm going to take this together. I only have 1 on the reactant side, but on the product side, I have a total of 3. Right. So as it stands right now, the only thing that's balanced is the hydrogen. So we need to balance out the aluminum and the sulfate. So notice we have 1 aluminum here, 2 on the product side. This one's easy to balance. We just put a 2 out in front of here. This is now balanced. And so now we need to look down to balance out the sulfate. Notice we have 3 sulfates on the product side, 1 on the reactant side. So we need to put a 3 out in front of here. But of course, by doing that, we also change the number of hydrogen ions. And so now we have a total of 3 times 2, which is 6 hydrogens here, and only 2 on the product side. However, we now have 3 sulfates on the reactant side, and we also have 3 sulfates on the product side. And so the last thing we need to do then, we have 6 hydrogens here, only 2 here. 6 divided by 2 is 3. And so we need to put a big 3 out in front of here. This changes this to a total of 6. And so now that these are all balanced out, this now is our balanced chemical equation between aluminum and sulfuric acid. So these are going to form aluminum sulfate plus hydrogen gas. And so whenever you have a metal plus an acid, you will always form a salt and hydrogen gas. And so that is for part A of number 1. And so let us go ahead now and do part B for this problem. Part B, we're going to now react calcium carbonate and hydrobromic acid. So calcium carbonate and hydrobromic acid. All right. first thing we need to do is figure out the formulas for each of these. Calcium as an ion is going to be Ca2+. Carbonate, which was one of those ions, polyatomic ions I had you guys memorize, is CO3 2-. And so notice, in this case, the charges will balance out, so we can get rid of these and just make it as CaCO3. And means plus. And then hydrobromic acid is HBr. So remember, hydrochloric acid is HCl. Hydrobromic acid is HBr. Right. We have our two reactants that will come together then to form two new products. And so notice that in this problem, we're going to have a double replacement type reaction. And so these, the C and the H, are going to switch places, and the Br and the CO3 are going to switch places. And so we're going to end up with two new products. We're going to end up with H. And so notice in this problem, we have H plus, CO3 2-. These will not going to balance out, so again, we need to do crisscross. The 2 is going to come down here. The 1, we don't have to do anything more with that, so this is H2CO3. So these have switched here, and so now we have CaBr. So Ca again is 2+, Br is -1 because it's a halogen. Notice that these are not going to balance out, so again we have to crisscross, and so we're going to end up with CaBr2. All right, and so if we look at this reaction, we can see that it's not quite balanced. And so we need to go ahead and make sure to balance that. So notice we have calcium. I'm going to keep the carbonate together just to make it easy on myself. So this is CO3. I have hydrogen, H. And I have bromine, Br. Right. On the reactant side, I have just one calcium. On the product side, I also have one calcium. So these balance out. Carbonate, I have one on the reactant side. And on the product side, I also have just one. Hydrogen, on the reactant side, I have just one. On the product side, however, I have two. So those aren't matching up yet. Br, bromine, I have one on the reactant side. Over here on the product side, I have two. All right. Notice that the calcium and the carbonate balance out. The hydrogen and bromine do not. However, notice that they are both half of what they are on the reactant side and on the product side. So the easy way to balance this out is just to simply put a large number 2 in front of the HBr. And so by doing that, we now have two hydrogens. Remember that the 2 distributes to the bromine, so we also have two bromines. And so now we have our balanced chemical equation. So we have calcium carbonate. We're adding hydrobromic acid to that. We're going to be forming carbonic acid and calcium bromide. Because remember, the ending changes. So this is calcium bromide. And so that is the answer then for 1 part B. And so hopefully that made sense. All right, we're going to go ahead and then do problem number 3, and then we'll be done then for today. All right. Problem number 3 is going to be located on page 640. And part 3, number 3 has 3 parts. So I'm going to go ahead and we'll do 3 part A first. For all of these questions, they want us to identify the conjugate acid-base pairs in each reaction. And so our first reaction is NH4 plus OH minus goes to equilibrium NH3 plus H2O. I want to introduce an important feature here. You'll notice that we don't have an arrow that just points to the right. We have an arrow that goes to the right then we also have an arrow that goes to the left. And so in this type of problem, we refer to this as an equilibrium problem. So this reaction is going on this way, but then the back reaction is also going on as well. And so the double-headed arrow here tells you that this is an equilibrium reaction. And so what we need to do first is to identify the acid and the base, and then we can determine what the conjugate acid and conjugate base are. All right, remember that in these problems, the acid and the base will be on the left, the reactant side, and the conjugate acid and conjugate base, therefore, will be on the product side. So if we look at our equation, we see, for example, that NH4 plus 1 over here becomes NH3 nothing. And so this would be our acid, and therefore this would be our base. Because this has lost a hydrogen ion, this is now our conjugate acid, or base, I'm sorry, this is conjugate base. And therefore the water is the conjugate acid. And so again, I want to point out that the acid and the conjugate base go together, and the base and the conjugate acid go together. So this goes with this, and this goes with this. And so notice that that's how we're able to distinguish that. So the acid and the base will always be on the left side, the reactant side. The conjugate acid, conjugate base will be on the product side, the right side. And so the acid goes with conjugate base, and the base then goes with the conjugate acid, because this has now picked up an additional hydrogen to form water. All right, let's look then at part B. Part B, we're going to go ahead and identify the conjugate acid-base pairs for this reaction. We have hydrobromic acid plus H2O. Again, is in equilibrium with H3O plus Br minus. All right. Notice I already said that this is hydrobromic acid, so I've identified this as the acid, and therefore you know then that the water here in this case is acting as a base. I do want to point out that water, again, is a very unusual substance. Water, in some cases, can act like an acid to donate a hydrogen ion. Sometimes it acts as a base by accepting a hydrogen ion, and so water is an example of what's known as an amphoteric compound. And so just to let you know what that means. All right, and so notice that here, the acid, over here, it's lost the hydrogen, and so we know that the Br minus must be the conjugate base, because it has lost the H plus that the HBr had. Also, the water here is the base. Over here, it's picked up a hydrogen ion, and so therefore this is going to be the conjugate acid. And so again, I want to point out that the acid goes with the conjugate base, and the base goes with the conjugate acid. And so that's how that works. All right, one more problem, and then we'll be done for today. Part C. We're going to go ahead and identify the conjugate acid-base pairs in this chemical reaction. CO3 2- plus H2O, equilibrium, HCO3 minus plus OH minus. All right, so again, we remember that the acid and base will be on the left, the conjugate acid, conjugate base will be on the right, and so we have to look to see where the hydrogen ion is moving to in order to determine which is the conjugate acid versus the conjugate base. All right, notice in this problem, we have CO3 2-. Over here, we have HCO3-. And so notice that this species has picked up or accepted a hydrogen ion. So we know, based upon the Bronsted-Lowry definition, that this must be our base. Because over here, that would be where it's picked up the hydrogen ion. Therefore, the water in this case is not a base like it was in the last part, but it's actually acting as the acid. Because we know that bases and conjugate acids are paired together, we know that the HCO3 must be the conjugate acid. And the acid here, which donates one of its hydrogen ions then to the base, this therefore, because it lacks the 1H plus ion, is the conjugate base. All right. And so again, we can see the acid goes with the conjugate base, and the base here goes with the conjugate acid. All right. And so again, the acid and the base will always be on the reactant, the left side. The conjugate acid, conjugate base will be on the right. The acid and the conjugate base are joined together, and the base and the conjugate acid are therefore joined together. And so with that, we're going to stop here for today. And so tomorrow, we'll learn a little bit more about strengths of acids and bases. And so I hope you guys learned some things, and I will talk with you guys again soon.